So for today, we'll be doing section 11 in our course, or lecture 11 in our course, and it's uh, titled Power Series and their Convergence. So I hope you have watched the lecture associated to this topic. Okay, but let us recall some basic concepts of power series. So first, the definition of the power series. So a series of the form sum from n equals 0 to plus infinity of c sub n x minus a to the n, and this is expanded as c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus so on, where x here, it's a variable, and a is a fixed real number, and your C sub 0, C sub 1, C sub 2, etc., they are constants. Okay. This one is called a power series centered at A, or power series about A. Okay. So if you look at the expansion, okay, we are using the following convention. So whatever your x is, x minus a to the 0, it's always equal to 1. So we use this even if your x equals a. So take note, 0 to the 0, it's not a number. Okay? But in this form, if we are talking about power series, we'll just consider this guy here, x minus a to the 0 equals 1, even if your x is equal to a. So that's why in this expansion, you only see c sub 0. It's a constant. And then plus c sub 1 with the um, term x minus a plus blah, blah, blah. Okay? Now, a powerful theorem that tells us where the power series converge is the following. So, given a power series, okay, in this form, there are only three possibilities, and only one of these is true. Okay? So, first is the series converges only at x equals a. And then second, the series converges for all real values of x. And the third, there is a positive number r such that the series converges if absolute value of x minus a less than r, and the series diverges if the absolute value of x minus a is greater than r. Okay? For the first case here, we say or we define r equals 0. Okay, that is um, if the series here converges only at x equals a, we say that r equals 0. Okay, for the second case, meaning if the series converges for all real values of x, we define r to be plus infinity. Okay, and of course, for the third case, there is that positive number r will be obtained. Okay, we call this r the radius of convergence of the power series. And then the set of values of x for which the series converges is called the interval of convergence of the power series. Okay, so um, let me just recall what this means here. So this means absolute value of x minus a less than r. Okay, you have negative r less than x minus a less than r. Okay, actually this is an if and only if statement. So uh, from here you can go to this, or from this you can go to the one above here. And then if we further calculate this, we will have x is greater than a minus r, but less than a plus r. Okay, so this guy here means that if we are in the third case, this means that the power series, okay, This means that the power series converges on the interval um, a minus r, comma, a plus r. Okay, that's for sure. The problem now is what about the endpoints? Okay, so if we are going to find the interval of convergence of the power series, aside from getting this interval, we have to check the convergence of the endpoints, a minus r and at a plus r. So possible interval of convergence, okay, P IOC. So there are four possibilities. You have the closed interval a minus r comma a plus r. You also have the half open interval a minus r comma a plus r. The other half open interval here, okay? And then finally the open interval, okay? So these are the four possibilities, okay? Now, once you have obtained this inequality here or this interval here, a minus r comma a plus r, okay, or once you have obtained the endpoints of your interval, you don't have to list down all these four possibilities. Just go directly to the testing of the endpoints, okay? So that will minimize the solution. Okay, so you can compute for this interval. Okay, and once you have the endpoints, just go directly to testing the endpoints. And as you have seen in the lecture, in order to find this interval as well as the radius of convergence, we only use, or most of the time we used ratio test. So you have to recall the conclusions for the ratio test. Of course, the hypothesis also. Okay, so let us work on the examples I have prepared in here. Okay, let's start with this. So in all of the examples here, our job is to determine the radius of convergence and the interval of convergence of the given series. Okay, so we have this series, sum from n equals 1 to plus infinity of x to the n over n to the 4 to the n. So in here, we label these terms as our a sub n, and then we calculate the limit as n approaches plus infinity of the ratio a n plus 1 over a n in the absolute values. Okay, and this is equal to the limit as n approaches plus infinity. That's right, a sub n plus 1. You will have x to the n plus 1 divided by n plus 1 raised to the fourth power 4 raised to n plus 1. And then for the denominator a sub n, let's just get the reciprocal of this. So we multiply. So we have times n to the 4 to the n divided by x to the n. Then we close that absolute value. Okay? And for this guy here, 4 raised to n plus 1, you can rewrite this as 4 raised to n times 4. So this guy here will cancel this 4 to the n. Okay? And then, what else? This x to the n here will cancel the x to the n in this part. Okay? X to the n in this part. So I'm using shortcuts in here, but more formally, what I actually did there was to write x to the n times x, and then for the other guy, on the denominator I had there 4 to the n times 4. So you can do the cancellation. This one, if you do this, it's totally fine with me. Okay, but it's not always like this. Okay, it's not always like this. You will realize that you will need to expand or decompose your terms. So anyway, so from there we do the cancellation, and what's left inside, so we have the limit as n approaches plus infinity. We have x, and then we have over 4. So this x here, this 4 here, and then let's combine this n to the 4 and n plus 1 to the 4. So times n to the 4 over n plus 1 to the 4, and we have the absolute values in here. Okay, take note, your x over 4 here, it's independent of n. So you can bring this out. Okay, you can bring this out of the limit. Furthermore, since x is a variable, you have to retain the absolute value for x. Okay, so meaning you will have x to the 4 over 4 times the limit as n approaches plus infinity. And then for this, since you are taking positive values for n, you can just remove the absolute value for this guy here. So anyway, you will get n to the 4 over n plus 1 to the 4. Okay, and for this guy here, you can just write it. You can just write it as n over n plus 1 to the 4. Okay, so it's easier to calculate the limit. In fact, in this form, the limit can be calculated easily. But in this form here, it's more obvious. Okay, it's more obvious. They are practically the same anyway. So you have absolute value of x over 4, and the limit of this, so both of them, degree 4, and the leading coefficients of the numerator is 1, the leading coefficients of the denominator is also 1. So the limit is just 1 over 1, or it's just 1. Okay? So the limit of a sub n plus 1 over a sub n in absolute values is equal to absolute value of x over 4. Now, we want this series to be convergent. And in order for this series to be convergent, we need this absolute value of x over 4 to be less than 1. Okay? So from here, you will get absolute value of x less than 4. Okay? And from here, you will see immediately the radius. Okay? You will see immediately the radius. So from here, radius is equal to 4. But as an interval without the absolute value symbol here, we just have negative 4 less than x less than 4. Okay? So question so far. Okay? So now we have the interval for the x. Negative 4 up to 4. So we test this negative 4, and we also test this 4. Okay? So when x equals 4, we have the series sum. Okay, we have the series sum 4 to the n over n to the 4 4 to the n, 4 to the n from 1 to plus infinity. But this is just series from 1 up to plus infinity of 1 over n to the 4. And this is convergent. This guy here, it's convergent. Convergent because it's just a p-series. Okay? Convergent since it is a p-series with p equals 4, which is greater than 1. Okay? So the right endpoint, okay, the right endpoint is included in the interval of convergence. For the other guy, when x equals -4, we have the series -4 to the n over n to the 4, 4 to the n from 1 up to plus infinity. This is equal to the sum, -1 to the n over n to the 4, n from 1 up to plus infinity. Okay? And then you see this is an alternating series. Okay? So you can use your alternating series test. Just confirm the conditions. Okay? But we can also consider, so if we consider the series with the absolute values, okay, absolute values of -1 to the n to the 4, and from 1 up to plus infinity, this is just the series, this guy here, 1 over n to the 4, and from, oops, and from 1 up to plus infinity, okay, which is convergent, same as above. So let's just write convergent, same as above, which means this guy here is absolutely convergent. Okay? So the series -1 to the n over n to the 4, and from 1 up to plus infinity is absolutely convergent. Okay? So therefore, all in all, therefore, the interval of convergence, the IOC, is the interval, closed interval -4 up to 4. Okay? Question? Okay. So let's look at our next example here. So this time we have the series from n equals 0 to plus infinity of quantity x minus 2 raised to the n over n squared plus 1. Okay? So again, just like before, we label this as our a sub n, okay? Which means if we want to find the limit, absolute value of a n plus 1 over a n as n approaches plus infinity, this is equal to what? So the limit as n approaches infinity, and then for this guy, we have x minus 2 raised to n plus 1 divided by n plus 1 quantity squared plus 1 times over, so we have 1 over a sub n, so we'll just get the reciprocal of this. So times n squared plus 1 divided by x minus 2 quantity raised to n. Okay? And then just like in the previous solution and in several examples that you've seen, so this guy here, x minus 2 raised to n plus 1, you can decompose this into x minus 2 raised to n times x minus 2. And then the x minus 2 raised to n will cancel this guy here. Okay? And then you can take out that x minus 2, okay, outside the limit, but don't forget to write the absolute values. So I will do that, and you can actually do this. You can actually do this, okay? From this step going to this step, it's totally fine with me. So the limit as n approaches infinity, and then we have the absolute value of, oh, we can remove the absolute value symbol for this part because anyway, what remains inside this absolute value is positive. So let's just remove that absolute value symbol, and you will just have something like this. So n plus 1 quantity squared plus 1. And again, as n approaches infinity, this just goes to 1. Okay? Which means that this is just absolute value of x minus 2. And then we want this series to be convergent. So we make sure that this guy here is less than 1. So from here, again, you will see that r equals 1 here. Okay. By the way, for emphasis, box this part, telling me that you have already obtained the radius of convergence. So going back to this example, let's just box this part here. Okay. So continuing from here, okay, so you will have absolute value of x minus 2 less than 1. This means that you have negative 1 less than x minus 2 less than positive 1. And then adding 2 in all parts of this inequality, you will have 1 less than x less than 3. Okay? Question? So, we have the interval. Okay? Definitely, this series will be convergent in this interval. But we need to check the endpoints. Okay? We need to check the endpoints. So, in here, when x equals 1, we have the series negative 1 to the n over n squared plus 1, n from 0 to plus infinity. Okay? And then what? This is alternating series. This is alternating. So alternating series. Okay? But anyway, instead of using alternating series tests, we'll use absolute convergence tests. Okay? So we consider Instead, we consider the series of the absolute values, -1 to the n over n squared plus 1, and from 1 or from 0 to plus infinity. But this is just the series 1 over n squared plus 1 and from 0 to plus infinity. And then from here, you can use your comparison test or your limit comparison test in order to determine the convergence of this series. Okay? Let's use limit comparison test. Okay? So compare with the series 1 over n squared and from 1 up to plus infinity. So anyway, this one starts with n equals 0. You can just decompose it and then just just start with n equals 1. Okay? So you can do the comparison with this series. Compare with this series, which is convergent, since it is a p series with p equals 2 greater than 1. Okay? And then we take the limit of 1 over n squared plus 1 all over 1 over n squared as n approaches plus infinity. Okay? Or this is just the limit as n approaches plus infinity of n squared over n squared plus 1. And this is equal to 1. Again, second degree polynomial in the numerator, second degree polynomial on the denominator. So just look at the leading coefficients. Since the limit is equal to 1 and this is greater than 0, by limit comparison test, the series 1 over n squared plus 1 n equals 0 up to plus infinity, this is convergent. Okay? And therefore, and so the series -1 to the n over n squared plus 1 and starting from 0 up to plus infinity. And so this one is also convergent. Okay? It's absolutely convergent, but we just need the convergence. Okay? And so this series here is convergent by absolute convergence test. So let me just put this guy here. So we include x equals 1. Now, when x equals 3, we have the series. So 3 minus 2, that's just 1. So you have 1 over n squared plus 1, and from 0 to plus infinity. And that's precisely this guy here. Okay? So following the same argument as above, actually we are not just going to follow it. We copy the same argument, you know, because you're just gonna use this. So from here up to this part here, it's exactly the same. So anyway, following the same argument as above, series 1 over n squared plus 1, and from 0 to plus infinity is convergent. Or maybe you can say that we have shown in this step that this is convergent. So you can also write that way. So therefore, we now have the IOC. Therefore, the interval of convergence is the closed interval 1 up to 3. Okay? Question? Next example. Let's go. Now we have the sum from n equals 1 to plus infinity of this guy here. N over 2 to the n times n squared plus 1 x raised to n. Okay? So again, we label this as our a sub n. And what do we get? We have the limit absolute value a sub n plus 1 over a sub n. As n approaches plus infinity. And this guy here, let us plug in. So for the first one, you will have n plus 1, x to the n plus 1. So this is your n plus 1 here, the x to the n plus 1 coming from this. And then divided by, you have 2 to the n plus 1, quantity n plus 1 squared plus 1. Then times the reciprocal. Let me adjust this. Okay. So times the reciprocal. So we have 2 to the n times n squared plus 1 divided by n x to the n. So close absolute value. Okay. And then in here, you have 2 to the n and then the 2 to the n plus 1 in here. So 2 to the n will cancel. Here you have x to the n plus 1, and then you have x to the n, and therefore your x to the n will cancel. So this guy here, we can simplify into the limit as n approaches plus infinity, okay, of x over 2, okay, x over 2 in absolute value. So again, this guy here and this guy here, it's this part here and this part here. And then for the rest, for those n's, let's just copy. Okay. So we will have n plus 1, n squared plus 1 divided by n times n plus 1 quantity squared plus 1 in absolute values. Close parenthesis here. Then just like before, this x over 2, we can bring it out. So you have absolute value of x over 2. And then we have the limit. As n approaches plus infinity, again, just copy. So you have n plus 1. And then here you have n squared plus 1. For the denominator, you have n. and then you have n plus 1 squared plus 1. So again, this is in the numerator, you have a third degree polynomial after multiplication here. And also for the denominator, you have a third degree polynomial after multiplication here. Furthermore, the leading coefficient in the numerator is 1. In the denominator, it's also 1. So the limit as n approaches plus infinity for this guy, it's just 1. And therefore, we have only absolute value of x over 2. And if we want this to be convergent, we want this to be less than 1. Okay? So this means you have absolute value of x less than 2, which means your radius is equal to 2. Following? Okay, so from here, you have negative 2 less than x less than positive 2. So the endpoints are negative 2 and positive 2. Okay, so let's start verifying, or let's start determining the convergence at the endpoints when x equals 2. Let's start with x equals 2. So when x equals 2, your series will just be, so the series from 1 up to plus infinity of n times 2 to the n, that's your x of x equals 2. So you have your 2 to the n divided by 2 to the n times n squared plus 1. And you see this is just the series n over n squared plus 1. N from 1 up to plus infinity. And what do you do for this? We can use comparison test or limit comparison test. Yeah? So compare with what? So you have a polynomial in the numerator, it's just n, okay? And then on the denominator, you have a polynomial n squared plus 1. So you take the leading term in the numerator. You also take the leading term on the denominator, okay? And then you simplify. But the leading term in the numerator, it's just n. The leading term in the denominator, it's n squared. So n over n squared, you just have 1 over n. Which means you compare this with the harmonic series, 1 over n, n from 1 up to plus infinity. This is divergent. Divergent because this is the harmonic series. Okay? And then, now, you get the limit. Limit of, let's say you have n over n squared plus 1 divided by 1 over n going to plus infinity. But this guy here, it's just the limit as n goes to plus infinity of n squared over n squared plus 1. And we've been doing this since the beginning. Well, we have a lot of, actually the previous example, it's just this one. But anyway, the limit is just 1, and this is greater than 0. Which means this guy here, it's divergent. So the series n over n squared plus 1, and from 1 up to infinity is divergent by comparison test, by limit comparison test, Okay. Question. Now let's look at the other endpoint when x equals -2. So let me go to the next screen. When x equals -2, we now have the series n times -2 to the n over 2 to the n times n squared plus 1. And from 1 up to plus infinity. But this guy here, you can take out -1 to the n. So you will have -1 to the n times 2 to the n. And that 2 to the n will cancel the 2 to the n in the denominator. So this series becomes -1 to the n over n squared plus 1. And from 1 up to plus infinity. Now we will use alternating series test for this. We know that n over n squared plus 1, it's always positive. Okay? Then let's check if it is decreasing. And let us show that the limit of this is equal to 0. Okay? So let f of x be equal to x over x squared plus 1 for x in the interval 1 up to plus infinity. Okay? So f of x is greater than 0 for all x, for x greater than or equal to 1. So we have positivity. Also, f prime of x here, so we get the derivative to show that this is decreasing. We want our first derivative to be less than 0. But anyway, f prime of x, it's low, derivative of high. So you have x squared plus 1 times the derivative of high. This is just 1. And then minus high. So minus x times the derivative of x squared plus 1. The derivative is just 2x. All over low squared. So x squared plus 1 here. Quantity squared. And if we simplify this, we'll just get 1 minus x squared over x squared plus 1, quantity squared. And clearly this is less than 0 for x greater than 1. Okay? Hence, so f is decreasing. Decreasing on the interval 1 to plus infinity. Moreover, we now get the limit. Moreover, the limit of f of x as x goes to plus infinity. So this one here, limit of x over x squared plus 1 as x goes to plus infinity. You can use your L'Hopital's rule if you want, or you can argue that the degree in the numerator is less than the degree of the denominator, which means the limit must go to 0. Okay? Since the degree of numerator is than less than the degree of denominator. Okay? Therefore, by alternating series test, so by alternating series test, this series here is convergent. The series -1 to the n over n squared plus 1, and from 1 up to plus infinity, this series here is convergent. Okay? Which gives us the conclusion that the interval of convergence is. So earlier, at +2, we have a divergent series. So we do not include this +2. And for the -2, the series is convergent. So the IOC contains, or is the half interval -2 up to +2, including -2, but not +2. So this is our interval of convergence. Okay? Question? Next. We now have the series x plus 2 to the n over 2 to the n ln of n. Okay? So again, we'll have this as our a sub n. Then we look at the limit as n approaches plus infinity, absolute value of an plus 1 over an. I think I will have to adjust this to a lower location. Yeah, this one is fine. And then we plug in limit as n approaches plus infinity, absolute value. You have x plus 2 quantity raised to n plus 1 divided by here 2 to the n plus 1 ln of n plus 1 times you have 1 over a sub n, so we take the reciprocal of this. You have 2 to the n ln of n divided by x plus 2 raised to n. And just like before, 2 to the n will cancel the 2 to the n in here. We'll be left with 2. In here, we'll cancel x to the x plus 2 to the n with this, and we will be left with x plus 2. Okay? So, and then after doing the cancellation, we will bring out that x plus 2 over 2 because, again, they are independent of n. So you will have absolute value of x plus 2 over 2. And what's left inside, okay, it's the term ln of n divided by ln of n plus 1. Okay? And then for this guy here, it's not straightforward, but you can use your L'Hopital's rule. So yeah, let's not change this index here, but we will assume that this, although the variable is n, we will assume that they are the continuous functions. Okay, meaning including all numbers in between integers. Okay, just to avoid the double variable in here because we already have the x in here. So anyway, let's use your L'Hopital's rule here. So you have absolute value of x over 2, or x plus 2 over 2, and then the limit as n approaches plus infinity. So we use the L'Hopital's rule for this part. We'll have 1 over n for the numerator. For the denominator, you have 1 over n plus 1. And then rewriting it, we'll have x plus 2 absolute value, and then over 2. This is just the limit as n approaches plus infinity of n plus 1 over n. And again, this guy here, you can even separate this numerator into two parts, and you will immediately see that the limit is equal to 1. Therefore, the limit of the absolute value of a sub n plus 1 over a sub n, it's absolute value of x plus 2 over 2. And just like before, we need this to be less than 1 so that this guy here is convergent, which means from this here, we have absolute value of x plus 2 must be less than 2, which tells us that r, this is equal to 2. Okay? And then from here, we separate or we remove the absolute values. So we'll have negative 2 less than x plus 2 less than 2, which gives us the interval negative 4 less than x less than 0. Okay? So this is our interval. Now, we check the endpoints. Okay, we check the endpoints. Let's start with negative 4. So when x equals negative 4, you'll get the series negative 2 to the n over 2 to the n ln of n from 2 to plus infinity. Or simply, you will have the series negative 1 to the n over ln of n and from 2 to plus infinity. So we can use alternating series test here. So we know that 1 over ln of n, okay, we know that this is greater than 0 for n greater than or equal to 2. What else? We know that as n increases, ln n increases, and so 1 over ln n decreases. And so 1 over ln n decreases. And then you have the limit of 1 over ln n as n approaches plus infinity. This is equal to 0. So by AST, the series, that alternating series, negative 1 to the n over ln n n from 2 to plus infinity is convergent. Okay? For the other guy, I'll leave that to you. You check that when x equals 0, the series obtained will be divergent. Okay? So when x equals 0, we have the series 1 over ln n. N from 2 to plus infinity. Check this is divergent. This is divergent. Okay? So check this or verify. So the IOC is, so negative 4 is included, but 0 is not included. So you have this interval. Okay? Question? So for our last example, let us consider this power series. Now, observe that all the expressions here in the term of the power series have exponent n. So you see here, x minus 2 raised to n, and the denominator is n raised to n. So instead of using ratio test to find the radius of convergence or the interval of convergence of this power series, we will use root test. So remember, root test and ratio test give the same conclusion. Okay? And in both tests, we compare their respective limits to 1. So convergent if the limit is less than 1, okay? And divergent if the limit is greater than 1. So we can use also root test in this particular case or in this particular example to be able to determine the radius and the interval of convergence. Okay? So in here, let us take this as our a sub n, and then now we are going to find the limit as n approaches plus infinity of the absolute value of an raised to 1 over n. But this guy here, this is just the limit as n approaches plus infinity of the absolute value of x minus 2 quantity to the n raised to n, okay? And then 1 over n. But notice this is just the limit as n approaches plus infinity of the absolute value of x minus 2 over n. Okay? And since your x minus 2 is dependent of n, you can bring it out. Okay? Or since it is independent of n, this absolute value of x minus 2 is constant relative to that n. And you see, as n approaches plus infinity, this will just go to 0. So this guy here is 0. And this is less than 1. Okay? This is less than 1. Therefore, the series here is always absolutely convergent for any x, which means that this is convergent everywhere. So by root test, the series x minus 2 raised to n over n to the n from 1 up to plus infinity is convergent everywhere. convergent everywhere. Which means that your R here, this is just plus infinity, and your IOC, the interval of convergence, this is from negative infinity to plus infinity. Okay? So, that's all for today's discussion. Thank you for staying, and I hope you've learned some techniques from this discussion. So, thank you, and bye bye.